Thanks for the invitation. It's just great to be here. So many friends from over the years, and it's great to all be back together. So what I'd like to talk about is my departure to the dark side, as Michael Unser would put it, and some work that we've been doing on trying to understand deep networks and build a foundation on which to build a theory that's based on spline, a very special set of spline functions called max-affine splines. So we're interested in prediction problems. Lots of people have been talking at this meeting about prediction problems. We have data x, and we'd like to learn a function f that can predict its label, right? Label y. And so the goal is to try to learn this function x, or f rather. And we in general, given some training data, xi, yi pairs, data label pairs, n of them, we try to learn some, through various means, some approximation parameterized by theta of this prediction function. And there are lots of ways to do this. Deep networks are a modern alternative to some of the more classical approaches, where you can think of the deep network, the inputs x at one end, and outputs are prediction y or y hat at the other end. Okay? And we know that deep nets do this in a hierarchical way. This has been talked about yesterday and today, where deep net is built out of these layers with using different kinds of components, fully connected layers, which are just matrix multiplies, convolutional layers, these thresholding layers called ReLU, pooling layers that downsample, and I'm just going to assume that people are familiar with these various layers. We're going to focus today primarily just on the matrix multiplications and these ReLU blocks. And the important thing is that each of these layers basically builds up one of our sub-functions or operators that we're using to create, in this compositional or hierarchical way, our overall prediction. Okay? And so we're going to study these individual blocks here. We're going to show that they're related to a special kind of spline, and therefore we can think of this overall deep network as a composition of these special kind of splines. This is clear to everybody, hopefully? Okay, so very, very special set of splines. So splines are very, very useful in this particular setup or setting. And let's just remind ourselves about splines. So a spline is a way of approximating a function. And there's really two parts to the spline. One is a partition. Right? We partition the input space. In this case, if x is just one-dimensional, we just partition it, in this case, into 4 different regions. And then once we have a partition, we just do a fit of some local mapping and apply that on each of these partitions. For example, here's the local mapping in this particular partition of the space. And this is an example here of a affine or linear spline. And we're going to focus exclusively on these kind of splines. So there's this yin-yang relationship, right, between the partition and the local mappings. And there are various different ways of finding spline approximations, right? There's the difficult way that's extremely powerful, which is the free knot spline problem, which is where the knots, if you will, or the partition is arbitrary. And so we're having to learn the locations of those cuts, if you will, or the knots. And this is extremely powerful, but extremely computationally complex to solve, right? It's basically impossible to solve for very large problems. And so typically in the past, we've resorted to some easier methods. For example, we just build out a grid, predefine the locations of the knots, or we think of doing wavelets, right? Which is a very special kind of dyadic partitioning type locations of the knots. So what I'm going to talk about is relating deep nets, layers of deep nets, to a very special kind of affine spline called a max-affine spline. Show of hands. Has anybody ever heard of max-affine splines? Okay? From you. Oh, okay. Oh, Nick has. Okay, great. So these go back to Stephen Boyd about 10 years ago, and they're just a very they're just a very, very useful tool in this So what are they? So let's consider building a piecewise affine approximation of a convex function using R regions. Okay? And let's assume, well, since it's a piecewise affine approximation, each linear mapping is just an ax plus b, right? Slope plus y-intercept. This is in higher dimensions than just one. We have R of these regions, okay? And here's an example with R equals 4, right? Let's just assume we have these A's and these B's and they're fixed. Slopes are fixed, offsets are fixed. So I've just plotted these four functions for some particular A's and B's. And now let's assume that we want to approximate a convex function over these regions. Okay, well then the key result in the max-affine spline setup is that you form the spline approximation simply by taking the maximizer of each of these linear pieces over the domain. So basically you just take the top line. Okay, so this is, you see we're taking A4, B4 here, then we switch to A3, B3, et cetera. Right? And the critical thing is where these lines cross, right, implicitly defines our partition. Very, very important. Right? So where these lines cross implicitly defines the partition of our space. Right? Now, I haven't talked about how we find the A's and B's, but the really important thing is once you have these A's and B's, there's a way to actually find this partition. Okay, clear to everybody? Okay, so let's just look at a simple example. Let's say that we take a one-dimensional input x, right, just a scalar, and we scale it at b. Okay, and then let's put that through a ReLU, right? Classic deep learning idea, simply a thresholding, right? It's just the max of 0 and ax plus b. Well, if you stare at this for a minute, you can see that this is basically a max-affine spline, where the parameters of the max-affine spline are a1, b1, both 0. That's the flat part. And a2, b2 are just going to be the some offset, and then the actual the offset and the scaling that you applied to your signal, right? So the thing that you should have in the back of your mind, right, this very simple example is that scaling and offset going through ReLU is a max-affine spline. Okay, function. We form an operator simply by concatenating, right? We go from a vector input x to a vector output, call it z, right? Simply by concatenating k of these max-affine splines. So the input dimension is d in general. The output dimension is k. We just have k separate max-affine splines with separate parameters. Now we have the parameters a and b become a tensor and a matrix, but the operates in the same way. Okay, why is this interesting? Well, if you look at basically virtually any deep net architecture that people use today, and the nonlinearities that people use today in deep nets, namely ReLU family of nonlinearities, absolute value nonlinearity, also pooling type operations that I haven't defined, but basically these downsampling operations, all of these can be written as a max-affine spline. Right? They're piecewise linear operators. And therefore, we can see that each of these individual blocks is a max-affine spline. So a deep net is simply just a composition of max-affine splines. Okay? So just reiterating that, standard deep net layers are max-affine spline operators. They're convex with respect to each output dimension, right, with respect to the input. And an entire deep net is just going to be a composition of these max-affine spline operators. And since it's a composition of a max-affine spline operators, of course, the input-output mapping of the entire deep net with, say, L layers is just a big affine spline. Right? Make sense? Okay. So in general, right, a composition of convex operators is not convex. So this is a non-convex operator in general through the entire deep net. This is just an aside. If you do want to make the input-output mapping convex, you can do that just by making every single layer, except the first, has to have positive weights. As long as the weights in the matrices are positive, everything will work out. Okay, but we're not going to exploit this anymore. Okay, so layers of deep nets are max-affine splines. A deep net is a composition of max-affine splines. And since we know we have max-affine splines, we know given the A's and B's, we're going to be able to find the partition, right? And that's really where things get interesting, right? Is to think about this partitioning that goes on of the input space of a deep net. Okay, so a few minutes ago, right, that given a fixed sets of parameters, these little a's and b's in this 1D example, you can think of these in higher dimensions as just the matrix from your, let's say, fully connected or convolution operation with an offset, right? A bias is added, and then going through a ReLU, right? These parameters, right, directly allow us to find the breakpoints of the spline. So we can find the very easy partition of a single layer. So a layer, let's say convolution followed by ReLU, that's one layer. We can find that's a max-affine spline. We can find the partition of that input space, right, which is a feature map. Moreover, if we concatenate several of these operators together, we'll have a partition of a partition of a partition, and we're going to have a non-convex partition of the input space. And this provides links, direct links between deep nets and all kinds of interesting ideas from geometry, vector quantization, k-means type algorithms, Voronoi type tilings that we think is, well, as you're going to see, there's a lot of very useful things you can do with this geometrical connection. So let's show a simple example in just 2 dimensions. This applies in any dimension, right? So like high-dimensional networks. But just for visualization, because we can't visualize what goes on in 10,000D, let's look at a 2D example. So let's look at a deep net that takes a 2-dimensional input, goes through a fully connected matrix multiply to 4-dimensional output, first layer, and then to a 3-dimensional layer, again by a matrix multiplication followed by a ReLU, and then finally to a 4-dimensional output because we're interested in doing classification. And each of these output nodes corresponds to one of our classes. So if we put in an input here that belongs to this class, we'd like to see these outputs be 0 and this class be either 1 or large. Okay, makes sense to everybody? Very simple network. Let's just take some training data. Here's 5,000 training data points from our. Remember, it was 2D, so we have an x1, x2 axis. This is we'd like to tell the difference between the green, the blue, cyan, and red classes. So we trained using approaches to learn the parameters of this deep net. Okay, what are these weights? But we're going to have a different sets of A's and B's for each of these different layers. Okay, so let's look at what happens. So this is our input in 2 dimensions. Now what we're going to do is look at the output of this first layer and see how this first layer max-affine spline operator partitions its input space, which in this case is a 2-dimensional space. And here's what we see.
Did you let the 45 be arbitrary?
Yeah, what do you mean?
Do you set it in the...
Oh, yeah, this is the architecture is just defined. This is just for illustration purposes. Okay, so this is the partitioning of affected by layer 1 of this network. Again, this is the layer that goes from 2 dimensions to 45 dimensions. And we see that it breaks, because it's just a MASO, it cuts the input space up into convex regions. And these convex regions are formed by hyperplane cuts, right, from the ReLU operation. Okay, so they're convex regions. And very, very important, now let's go back to the spline viewpoint. Okay, with inside each of these regions, right, there's an input to output mapping, which is a nonlinear mapping. But in fact, this mapping is very simple, because if I know that an input to this layer lives in this particular tile, let's call it a VQ tile, vector quantization tile, then I know that the mapping from this input to the output is just a simple affine transformation. right? That all inputs in this tile, all inputs belong to, they generate the same A matrix and offset B such that the mapping from any input in this tile to the output is just AX plus B, right? And this is splines, right? We have a partition within a partition, just a very simple mapping. Okay, make sense? Okay, so now let's look at what happens at the next region. Now this is with layers 1 and 2. 1 and 2 of our network. So now we went from 2 dimensions to 45 to 3. Now this layer subdivides, as we'll see, the partitioning of the first layer. And now you see it becomes much more complicated. In fact, some of these regions are now non-convex, right? But again, we have the exact same result, right? That if for a data that lives in a particular VQ tile, right here, right? All inputs in this, the mapping from this input to the output is, again, just a simple matrix times X plus an offset B, right? And each of these tiles has a different matrix A and a different vector B. Make sense? OK, so this is what happens when you learn. In this case, by backpropagation. There's the initialization on the far left. Typically set the weights or the matrix entries to random numbers. You set all the biases to 0. So we see we just cut the region up into cones. And you see as we're learning, right, by a stochastic gradient descent, the parameters of this network, we can actually look at how the VQ tiling is evolving, right, into these different shaped regions that are in some sense adapted to the data. Well, not in some sense, in a very real sense. Just have a look, for example, of the green and the red class and look at all of these cuts, right, that basically trace out the circle, right, between that separates the green from the, even though we're not, this isn't the decision boundary, you see we're already starting to learn a VQ tiling that's adapted to the input data, okay? So hopefully this kind of drives home with this simple example. So we can do let's talk about what we can do with all of this. So the first is you can show some interesting results. Let's talk about some theoretical results. The first is that this partition of the input space is a very special construct called a power diagram. Who's heard of a power diagram? Okay, it's basically the extension of a Voronoi diagram. Who knows about a Voronoi diagram? Voronoi diagram, you have a centroid, and then all points L2 distance from that centroid end up in the tile. Power diagram is simply you take that L2 distance and you make it what's called a Laguerre distance by adding just an extra parameter. It's called a radius parameter. And so it's very closely related to a Voronoi tiling, but it's this very special thing. We have a formula, right? There's a formula for all the centroids and radii of this power diagram. And the formula is just in terms of these A's and these B's. Okay, closed form formulas. And you can show pretty straightforward that the partition regions, these tiles, are always, for a single layer, are always convex polytopes.
Are you always assuming the A's and B entries are positive?
No. Absolutely. No. That was only just an aside. They're arbitrary. Yes, sir.
But I actually, to make a comment, because
yeah.
With splines, what's super important is that they are continuous.
These are also continuous, yeah.
But you know, when you make those max, it only stays continuous. I mean, this works because you're convex.
Yeah.
And you know, if you have a non-convex function, you have to be a little more careful.
Absolutely. But this is you should really just view max-affine splines as the jumping off point, because then it's a single and the mapping that you really might like to learn at that layer might be a non-convex mapping, but it's always stuck on doing a convex approximation.
Yeah, I mean I agree. At the end, it does exactly the tiling as you described, but I mean it imposes the continuity. Absolutely.
I
mean that's important.
Very important. And you can actually look at the really interesting thing is the way the cuts are formed in a way to preserve the continuity. Exactly. So in fact, the A's and B's on either side of a cut there's a formula for how they have to be related to each other, okay, which gives some really interesting insights. I don't have slides on it, but into like what's called weight sharing. So how the parameters in these the fully connected layer actually act sort of in concert, right, to build this tiling in a certain way. So that's a really good point.
So
Ron.
what are you doing other than saying these are the outputs of a neural network with a value and
Oh, well, what we're in a sense, this is simple.
the output
Yeah.
is a piecewise
Absolutely.
linear on some
Absolutely.
partition, and
So, but
what's the
so a few things. One is as you're going to see, because we can compute these, we can do things with these that are quite useful. Okay, so on one hand, I would say up to now it's just been primary visualization, right? Just what's going on with this partition, right? But this, when you look at this, you should start thinking, well, wow, maybe I should study the geometry of how these partitions are formed, because these partitions are basically doing some kind of almost like unsupervised learning of the data manifold, right?
control? It's like seeing how the parameters control the final
Absolutely.
output,
Yeah, absolutely.
like control points and
Yeah,
shades.
yeah, exactly. Yes.
Is it the final result in this?
No, this is just that first layer. This is not the final classification.
Final result.
Oh, I'll show that. I could pull a slide and show it later. Yeah. Okay, so let's keep going. Let's check the time. So you can also show that the way it's easy to show that the power diagram at input space to the deep net after the top of this layer, you can actually study with analytical formulas how this tiling is subdivided as we move layer through layer. This is an example just of layer 1 through layer 2 to layer 3 of a particular network. And you can study, since if you're doing classification, since the classification decision is basically made by a single level set cut, right, of the output function of the net, you can also study the geometry of the decision boundary. And this is now maybe where you might start thinking, okay, maybe I can think about how I'm approximating decision boundaries, right? And what constraints are imposed by deep net. Given I need to have continuity in this weight sharing from region to region, there's some very interesting results you can show. For example, the angle. How quickly can the decision boundary change when it moves from one tile into the next tile? There's actually constraint on that. Okay? Does that help, Ron? Okay, so this is some things you can think about as far as subdivision process. Let's look at other things we can do with this affine mapping. So just like I said earlier, since it's just a big affine spline, the mapping from the input to the output of the network is simply just, again, an affine mapping where there's a particular A and a particular B. Here's what the A's and B's look like for a convnet. Right? A big formula, but you can calculate everything. This is the A matrix, right? That's the output. A matrix times X plus this B offset vector. I left out an X here. So, no, there should be an X sitting up here. Okay, so we have a formula for this, and now we can do some interesting things with this formula. So first, let's look at this, visualize this AX plus B and ask what it really means, going from the input of our deep net to the output of our deep net, from X to this ZL. Okay, well, let's just to think a little bit about what this matrix A is. Well, this matrix A is just a matrix. How many rows does this have? It has a number of rows equal to let's say we're doing classification, the number of classes, right? Each row corresponds to a class. And now we can ask, what does this particular row of the cth row of this matrix look like? Well, let's just do some interpretation. What is how do we compute the output? Right? Well, the cth entry of that output is simply the cth row of A multiplied by X, right? Plus a bias, right? And when this is the correct class, what do we want that number to be? Big. When it's the incorrect class, what do we want that number to be? Small or 0. Okay? Well, this is precisely the match filtering. That's exactly what's going on in a deep net. right? Everything that goes on in radar and sonar. That basically we are building a match filter bank. A deep net is like a big it's a dictionary learning machine, right? That learns dictionaries such that when it basically constructs a signal-dependent match filter bank that's just right for that image. And you can actually visualize these. These match filters are closely related to what are called saliency maps, if you're a deep learning person. Here's an input. It looks like it's a plane. And here are just 3 different output channels, or 3 rows of that final A matrix, rather. Input-output mapping. For classifying this plane. So first, this is the row corresponding to the correct class. We built an image out of it. And you see if you squint, it looks like the plane. And here's the inner product, big number. Okay? Now if you continue to kind of squint, here's the ship class. And it kind of looks like anti-plane. In fact, this is the inner product, small number. And here's the dog row. Again, small number. Okay? And so there's basically we're building up this match filter bank, right, through these layers in a hierarchical way. Okay? So that's one useful thing you can do. And now you can study these saliency maps, which are, again, we have analytical formulas for what they are based on given input. So another thing you can do is you can think of defining new kinds of distances. Right? So as an example, we can capture the geometry, right, between the underlying manifold geometry of our training data set in terms of this vector quantization partition. And vector quantization comes from information theory, right? And the important thing is that each of these tiles in the vector quantization is associated with a code, right? And this is how vector quantization coders work. If an X falls into this region, you don't transmit X, you just transmit the code for X, right? So it affects a compression and a quantization. So we can exploit this. It turns out that the codes for each of these tiles just turn out to be, when you flow an input through a deep net, you basically look at all of the ReLU units. And if for a given input, if the ReLU passed any given ReLU, you have a lexicographical order of these ReLUs. And if the ReLU didn't pass a signal through, it's a 0. And if it passed a signal through, it's a 1. That gives you a unique code book for this entire VQ partition. And now we can think about looking at the distance between signals in terms of the Hamming distance between those code words. And you can actually show that this VQ distance relates to manifold geodesic type distance on the training data of your network, right? And so if we think about these problems of trying to classify these 2 people, Ingrid and Anna, into 2 different classes, it turns out that this Hamming distance between these VQ partitions relates to the distance along these manifolds from one image to the next image. So continuing to think about image manifolds, you can use this affine parameterization to define complexity measures. So how do we, going back to yesterday, Ron's talks and others, how can we quantify how complex the mapping is from an input to an output of a deep net? There have been all kinds of different measures. One of them has been counting the number of regions, for example, linear regions that are formed. Another is to exploit ideas from differential geometry. And in particular, there's a method developed about 15 years ago by Dave Donahoe and Kerry Grimes called the Hessian eigenmap method of manifold learning. And we can use this as an inspiration to quantify the complexity of the prediction function. So the mapping from an input of a deep net to some output of the deep net. And without going into the details, it's basically we take our prediction function over our data, and we look at the integral of the norm of the tangent Hessian at that point to the image manifold. Okay, it's a very natural measure of curviness. If the manifold is linear at that point, this measure is 0. If it's really curved, it's a large number. Okay, and moreover, you can approximate this. Using Monte Carlo type, basically by computing samples of this, using your training data to compute a sampled approximation to this particular integral. Okay, and it can be useful. Here's why it can be useful. Let's talk about data augmentation. How many people know about data augmentation? Show of hands. Okay, so when you train a deep network, typically people don't just train with the training data. And let's talk about image classification or face recognition type problems. They don't just use pictures, right? Pictures of Ron. They also augment the data with translates of the pictures of Ron, rotations of the pictures of Ron. Okay, why is this done? Well, it's a heuristic, and it's done because, well, two reasons. One is it generates more training data is plausible. These are all pictures of Ron. And in fact, if you think of these transformations like or transformations as, for example, translations, rotations, other kind of operations, all of these augmented pieces of data live on this same data manifold that the original sample did. So typically, you might take a set of 1,000 training images, and you will augment it by a factor of 1,000 to have 1,000,000 implicit training images when you do this training. It's very important for getting high performance. Okay, but this is a heuristic. Okay, well, it turns out you can prove fairly straightforwardly that data augmentation is doing but using a Hessian complexity penalty. Okay, so there's actually a Hessian complexity penalty hidden inside the data augmentation. And here's just some numerical experiments showing that this is the case. Here's the Monte Carlo approximation of this Hessian complexity measure. This is while we're learning the parameters of a network. Okay, so this vertical axis is complexity. Here is the complexity measure as we go through training with no data augmentation. So you see it's high. With data augmentation, you see it's really low. This is training data. This is on the test data. So the important thing is that doing data augmentation reduces the complexity of the function that is fit to the network. And there's all kinds of interesting things to explore from here. Ron. Yeah.
The data augmentation tells you the tangents to the manifold in some sense.
It's exactly. Exactly. Because those points. Exactly. Those points live nearby, right? Absolutely. But this, again, is why this might be useful to look at because you can compute, right? There's a formula, right, to compute these, again, given these spline parameters, right? Given these A's and given these B's. Okay, so let's wrap up. So the thing that I hope you take away is that this max-affine spline viewpoint, this coupling of local mappings, but really key, the geometry, right, of this VQ tiling provides a foundation on which to build, right, a theory of deep learning. And I would argue that a deep net is a vector quantization machine. That's the most important thing that a deep net does, is basically learning how to do free knot splines in 10,000 dimensions. How easy is that, Ron?
Well, I don't know why you say 10,000 dimensions. It's 2 dimensions, but you move up into high dimension and back down. The input to output is a two-dimensional function.
Yeah,
it is a high dimension because you try to classify.
Yeah.
It's the dimension of the number of pixels.
Yeah.
But I argue that it shouldn't.
But let's think about other data that isn't intrinsically an image. That's just 10,000 dimensional. How easy is it to do free knot splines on 10,000 dimensions? It's just not. Basically, this is what. It's a rhetorical question. Super hard, right?
No, but you end up with a partition if you're dealing with images.
Yep.
Right? You're going to end up with you're mapping a function of 2 variables.
Absolutely.
Into a function of 2 variables.
But what if you're in 10,000 dimensions? That's all I'm trying to. Yeah, this is difficult. And what deep nets are is just a particular way of finding this partition, right, in extremely high dimensional spaces. Okay, so summary. this is what we saw, that deep nets can be thought of as a composition of these max-affine splines. There's a geometrical link. We have this VQ-dependent mapping. There's a tie-in with matched filter banks. Lots of things that are classical from signal processing can be elicited out of this framework. And we can do all kinds of things with it, right, that we couldn't do before. There's a bunch of directions that we think are interesting. Studying the geometry of this VQ partition, difficult in high-dimensional spaces, but very, I think, very, very profitable future work. You can also look at stability. People have been talking about adversarial nets. You can actually calculate the constant to any point in the network if you know these A's and the B's of the mapping. I'll just mention a couple other things. Recurrent networks that are used a lot in time series type data. Turns out this theory covers recurrent networks as well. And it also covers non-piecewise affine activation functions. For example, sigmoid, classical ones like sigmoid, hyperbolic tangent. And the way that you do this is by thinking of the max-affine spline VQ tiling as a deterministic tiling, and then from which you can derive a mixture model, a probabilistic model, on top of that VQ tiling that allows you to think of what's called a soft vector quantization. So now a point only falls in a given tile with a certain probability. So it's a soft quantization. If you do this, it turns out that if you start with a hard VQ based on ReLU, you get sigmoid. Okay, so it's very natural. Class of nonlinear, oh, here we are. Here's ReLU. You get an infinite class of nonlinearities in between. And it turns out some of these are known, and some of these actually have been shown empirically to work better than either ReLU or sigmoid, better empirically. So this is an interesting space to explore. So I'll end saying there's some papers if you'd like to have a look, and I'd be happy to take questions. So thanks again.